section 9.4, we're going to discuss multiplying square roots together. Now again, it should be noted that while we are working specifically with square roots, as it's listed here in these notes, these rules can apply to any radicals that are multiplying together, and they work the exact same way. So starting off, our biggest and primary requirement for multiplying square roots or any radicals together is to make sure that the index of the radicals is identical to one another. So I have to multiply two square roots together, or two cube roots together, or two fifth roots, or anything like that. The indexes need to be the same. If the indexes are different, then I cannot multiply two radicals together, and I can't do anything with the problem that I've been given. It should also be noted that when we are going through this, while that is a primary requirement, when we do end up going through and multiplying radicals together, the index never changes in that process. It is only going to be the coefficients or the radicands that will be changing as we go through and multiply these square roots together or any other radicals together. Now the main rule and property that we are going to be applying here in this section is the product rule. And it states that if I have essentially two real non-negative numbers here, then the square root of those two numbers multiplying together can be broken apart into the square root of the first thing times the square root of the second thing. Again, this holds true if I have a third root, fifth root, 10th root, something like that, where I have a different index out front. But I can still split this product into two things inside of radicals multiplying together. Now we can also do the reverse of that. If I start off with two radicals that are multiplying together and the indexes are identical, then that means I can combine these together to be one single radical that we have here, where the radicands are going to then multiply together. It's fairly common that we see both of these show up, and they both have their uses as we go through and simplify expressions that are given to us. Breaking it down into these two different radicals might end up proving useful to say work with this number and then this variable and then a different variable, or maybe it ends up being the case, like in our second example, once I actually multiply everything together, now I can actually take the square root of the result. Sometimes we can, sometimes we can't. It all depends on the numbers that we've been given. So when we can identify and work with multiplying square roots together, it should be stated that the coefficients and the radicands are the only thing that are going to multiply together and actually change in this. So it's the number or variable that is out front of the radical, and then the radicands, the things again that are inside of the radical itself that could be changing. Those are the only two things that could be changing as we go through these problems. As necessary when you are going through these, it can be useful to simplify along the way if necessary. Sometimes we can, sometimes we can't, but oftentimes it does come down to the question of, do you want to simplify along the way or save the simplification for the very, very end of the problem? You're going to have to do it eventually, and on a case-by-case, problem-by-problem basis, that's going to be one that you're going to have to decide for yourself. Let's take a dive into a couple of these examples that we have here. Or actually, we'll take a look at all of them, and then see how we actually apply these properties. Looking at our first example, we have the square root of 14 times the square root of 12. This is a prime example of where we have the product rule coming into play and using that to get further along with this problem. As I look at this thing originally, I'm noticing 14 and 12 are not perfect squares, so I really couldn't do a whole lot to simplify these things down much further. You could look at the 12 and notice that, well, 12 could be broken down into 4 times 3, 4 being a perfect square, and then we could deal with that. You do have that option, but eventually we are going to need to multiply everything together. So because I can't simplify everything down all at once, or let's put it this way, I can't do this one all at once, I can't do this one all at once, we're just going to mash it all together to be one single radical. and then simplify that down from there. So when I make these one single radical, I'm going to get square root of 14 times 12. Now 14 times 12 is equal to, I'm doing calculation off screen here, it should be 168. There we go. And now I try and find the square root of 168, and we can use our method that we used in the previous videos, finding the prime factorization. 2 goes into that 84 times. 2, I want to say, what's that, 42? Yeah. I have to go with 3. 3 doesn't work, 5 doesn't work, 7 does work. Oops, should be a 1 there. All right. And then I have the prime factorization, again listed right here in this column. I'm looking for a perfect square, so it's going to be these two up here. And everything else is not a perfect square, so it's going to be leftovers inside the radical. So I'm bringing a single 2 out front. Everything inside that's left over is just going to multiply together, and that's going to give me 42. I can't do anything else from here to simplify the radicand down any further, so my final answer is going to be 2 times the square root of 42. Looking at example 2, we have 2 square roots multiplying together, and they have coefficients out front. So let's start with getting this thing consolidated down to being one single radical versus 2 of them. So if I'm multiplying everything together, I'm multiplying the coefficients together first. So that's going to be 2 times 3. It's going to give me 6. Remember that if the radicals are going to be multiplying together, that the index is not going to change, so it's going to stay as a square root. I then have 16 times 12 for the radicands, because those are going to multiply together. That's going to give me 192. And then I have x to the 5th times x to the 3rd. That's going to give me x to the 8th power. Make that a bit better x here. There we go. Now that everything's consolidated down to be one single radical, now I can go through and find the prime factorization of 192 and see what we get from there. Again, listing these things out. So 2 goes into this 96 times. 2 goes into that 48 times. 24, and so on. Again, you can find the prime factorization any way that you would like to. This is just a method that I have found over the years that works really, really well for me, and I like using it. So now I'm looking for perfect squares. I'm seeing I've got a perfect square here, a perfect square here, and I have a perfect square here. So all of these are going to come out front as individual 2's multiplying together. Then I have this 3 left over at the very bottom. That's going to stay inside the radical. We'll deal with the x later. So everything out front, we have 6 times 2, which is going to 12, times 2 gives us 24, and times 2 again gives us 48. So the coefficient becomes 48 times the square root of 3x to the 8th. Okay, now we can deal with this x to the 8th power. We're looking for perfect squares, so if you wanted to rewrite this as perfect squares, you could say it is x squared times x squared times x squared times x squared. So we have 4 of these perfect squares, which means those are all going to come out front as x times x times x times x. Or, instead of that big mouthful with it, we can just say x to the 4th power, and we have that 3 left over. Again, I have nothing I can do to simplify inside the radical any further. It's just square root of 3, and 3 is not a perfect square. So at this point in time, I have my final answer of 48x to the 4th times the square root of 3, and I'm done. For example 3, we have the quantity negative square root of 8, all raised to the 2nd power. Now when we have exponents showing up like this, I think it is very good practice to take a pause and determine what is being raised to the 2nd power. And what's being raised to the second power is everything inside this set of parentheses, which means everything inside here is going to multiply with itself. Now, my recommendation to you when you are doing this is actually to expand and write that out for yourself. What are the two things that are actually multiplying together? Make it abundantly clear what is multiplying out. This makes it clear if there are any signs that are multiplying together, especially if we have negatives, and also prevent the possibility of us inaccurately applying and canceling out a radical or signs or something as they show up. So now we have it looking like this, and now it's looking a lot more like the product rule that we discussed previously can come into play here. If I do that, the coefficients of -1 that are in front here, there's that invisible 1 that's hanging out in front of these problems. That's going to give us a +1, okay? And then the square root of 8 times the square root of 8, the radicands multiply together, and that's going to give me the square root of 64. And then 64 is a perfect square, so the square root of that is just going to be 8. So again, very, very useful. Take one extra line of work to expand what you started off with originally, and then see what all multiplies together, and then let the answer flow out from that. For example 4, we have some bit more complications that are showing up. The problems are starting to get a bit more advanced, and we have more things going on. So for number 4, we have this 5 out front multiplying to 7 minus 3 square root 5. So when we have situations like this showing up, we are going to be applying and using the distributive property. This 5 out front is going to multiply through to everything inside this set of parentheses. So 5 times 7, it's going to give us 35. And then 5 times the -3, it's only the coefficients that multiply together. It's going to give us minus 15. It's the square root of 5. We're looking to see, can I simplify the square root of 5 at all? 5 isn't a perfect square, so I can't really do anything with that. We then look to see, can I add or subtract these things together? And we can't, because one of them has a radical, the other one does not. So there's not a whole lot else I can do with this. And I have my final answer of 35 minus 15 times the square root of 5. Looking at number 5, we have a setup that's very similar to what we just saw in number 4. So just like we did in number 4, we are going to use the distributive property, and we are going to distribute the square root of 32 out to 4 and out to the square root of 2. Now, the square root of 32 times 4 is just going to result in 4 times the square root of 32. That 4 is going to multiply with the coefficient of the radical. And then with the square root of 32 and the square root of 2, they both have the same index out front of them, which is 2. It's invisible, but it's there. So I can multiply these two things together for the radicands and find that this creates the square root of 64. And we know that the square root of 64 is going to be 8. So let's just simplify that down now. So we're getting 8 there. Perfect. Now I need to look to see, can I simplify the square root of 32 at all? And like we've done in the past, we're going to find the prime factorization of 32. And as we go through this, we're finding, we've got some perfect squares showing up here. Perfect square here, perfect square here, and then I've got a leftover 2 at the very end. So these are going to come out front as 2's, multiplying with the thing in front of it, or the other coefficient there, I should say, with that 4. So I'm going to have 4 times 2, that's going to give me 8, and then that also multiplied by 2, which is going to give me 16. So I'm going to have 16 times the square root of 2 plus 8. Now for me personally, this is a small thing that I like to do to make sure I'm keeping all my work organized. I like to have the radical be the very last thing in my whole expression. So I'm going to do a very mild rewrite here and just make this 8 plus the square, or not square root, 8 plus 16 times the square root of 2, I should say. Get my words and my terms mixed up. This should be our final answer from here after a quick rewrite at the very end, and then we're good to go. Now we come to example 6, and we see that we now start to have 2 terms in our first parentheses and 2 terms in our second parentheses. The nice part about this is we're going to follow the same process that we've done with previous binomials, which is the first term multiplying through to everything in the second, then the second term multiplying to everything in the second set of parentheses as well. So we have 2 options here. Looking ahead and thinking ahead with this a little bit, we're seeing I'm going to end up having to multiply the square root of 32 and the square root of 28 together. 32 times the square root of 28 is going to get pretty darn gross. It's going to be a big number. I'm just going to do the calculation for that really quick here. 32 times 28, yeah, it's going to be 896. I don't really think we want to do the whole prime factorization table of 896. So we're going to take a quick detour, and let's go ahead and simplify these 2 things down before we do the distributive property. Might save us a little bit of time, or at least a little bit of headache later on, if nothing else. So if we have 32, I think we've done this one quite a bit as we've been going through these, but it's all right, we can do it again. So we're getting a perfect square here and a perfect square here. So we have 2 perfect squares and a single 2 left over. Let's take a look at 28 and its prime factorization. We know 2 goes into 28 14 times, 2 into 14 7 times. 2 doesn't go into 7, 3 doesn't go into 7, 5 doesn't go into 7, 7 does go into 7. We're good there. We're finding that we have yet another perfect square showing up here, and a single 7 left over. So I'm going to rewrite this square root of 32 and this 5 times the square root of 28 before I do the distributive property. And those things are going to become, looks like the square root 32 is going to become 4 square root 2. And I'm going to get 2 minus, I've got a single 2 that's coming out front here. That's going to multiply with the 5 that's already there. So that's going to give me 10 times the square root of, you have that 7 left over there. So now, looking ahead with this again, when I do the distributive property, I'm going to end up getting 2 times 7 showing up. That's going to be much nicer to work with compared to our previous numbers that we had. So now, let's apply the distributive property. This 1 is going to multiply through to everything in here, and this 4 times the square root of 2 is also going to multiply to everything in here. So as we do that, listing our results, we get 2 minus 10 times the square root of 7. And then we get 4 root 2 times 2, which is going to give us 8 root 2. And then we have 4 root 2 times negative 10 root 2. The coefficients multiply together. That's going to give us negative 40 out front. And then radicans are going to multiply together. And that's going to give me the square root of 14. I think I have, I have an error showing up in here. This should be 2 showing up here when this 4 multiplies through, or 4 root 2 multiplies through. We should only have an 8 out front, and this should be a 2 in here. Perfect. So now we're looking at this and we're saying, can I simplify any of these radicals and radicans down at all? Well, it turns out that none of these are actually perfect squares, nor do they have any perfect squares that could multiply into them. I'm also noticing that while the indexes for those radicals are the same, the radicans themselves are different, which means I can't do anything else with this problem, and therefore this big long string of stuff is going to be my final answer. Looking at number 7, this brings us into kind of combining what we did in example 3 and a bit of what we did in example 6, all in this problem now. So we have something being raised to the second power. That something is everything inside the set of parentheses. And as we did with example 3, I highly recommend to you expand this out for yourself. Write it out as everything in the parentheses times everything in the parentheses. A lot of people incorrectly think that they can, air quotes, distribute this exponent through to the square root and the 3. We cannot do that. Exponents do not apply and distribute the same way that coefficients do. We have to expand these things out, and then we can multiply everything together and see what our answers are. So once we have everything expanded, now we're just applying the distributive property. This 3 is going to multiply through to everything in the second set of parentheses. This negative square root 5 is going to multiply to everything in the second set of parentheses, and then we get our answers from there, and we can simplify stuff down accordingly. So 3 times 3 is going to give us 9. 3 times negative square root 5 is going to give me negative 3 square root 5. Then I have the negative square root 5 here multiplying to 3. That's going to give me another negative 3 root 5. And then finally at the very end we have a negative square root 5 times negative square root 5. Negative times a negative is a positive. Square root of 5 times the square root of 5 is giving me the square root of 25. And then in our next step, where we're simplifying some things down further, we determine that we combine like terms, 9 minus 6 square root 5, and the square root of 25 can become 5, so we can rewrite that there. I can now combine terms again with the 9 and the positive 5 adding together. I'm going to get 14 minus 6 times the square root of 5. Again, I'm always looking to see, can I cancel or reduce anything down any further? But because this square root of 5 is not a perfect square, and I can't find any prime factorization for it, this is going to be my final answer. So now, looking at our final example, if something's showing up where the first and last terms in both of these sets of parentheses are the same, and the sign in the middle is different. They're opposites from one another. So if you remember back to the previous sections and previous chapters where we had the difference of squares showing up, this is effectively a difference of squares problem, but we're given the problem at the beginning in its factored quote-unquote form. So if you're noticing that, great. If you're not, it's not really anything particularly important outside of kind of a coincidence that's showing up here. We're still going to apply the same thing that we did with number 7 and number 6 and number 5 with this, and that we're going to use the distributive property to multiply things through to get to our answer. So with this 4 in the first parentheses distributing through, we're going to get 16 plus 4 times the square root of 11. With the negative square root of 11 in the first set of parentheses multiplying through, we're going to get minus 4 root 11, and then minus square root of 121. Again, the last radicans multiplying together to give us 121 here. Now I'm combining like terms and simplifying things down as best I can. I have a positive 4 root 11 minus 4 root 11, meaning both of these are going to cancel out. And then I have at the very end the square root of 121. Square root of 121 is 11. So I'm just rewriting that here. Now I have 16 minus 11, and that's just going to give me 5. So it's a nice little fun bit that shows up here with this, is if we are noticing that we have the difference of squares in that factored form, then we're always going to end up getting just a single whole number answer, no radicals left over at the very end. And that's going to be showing up in some later sections when we take a look at those, but this is just a nice preview of what is to come later on. But all in all, for this problem, final answer is just going to be 5. So bringing things back together at the very end of the 9.4 material, I just want to summarize the quick stuff that we made a note of and that we applied throughout this section. Remember that when multiplying radicals together, the index needs to be the same. And when we are multiplying them together, the index never changes. It is only the coefficient and the radicands that are multiplying together. We did also have our product rule showing up. We most commonly see the two things multiplying together to become one thing. But again, if you were going through it and doing the reverse and breaking things down, you could be doing that as well. Otherwise, just take it slowly and steadily. Make sure you're correctly doing the distributive property as necessary with these problems, multiplying everything through as you're required to, and then show any and all steps that you need to as you're going through and solving these types of problems. So we got some extra group problems or practice problems if you'd like to give them a go on your own. Again, I'd recommend pausing the video here and then writing these down, trying them for yourself. Otherwise, we are going to scroll down here, right to the answers. And here we go. So that concludes everything that we've seen for the 9.4 material, multiplying square roots together.